I'm going to talk to you about the simple process of scaling up your DNA supply from research or discovery scale through development, GMP, and into commercialization using cell-free DNA, and specifically Touchlight's dbDNA technology. So first of all, who's Touchlight? We are a CDMO, first of all. We are an innovative CDMO. I guess, put simply, we are a classic CDMO. We work on a fee-for-service basis. We don't require licenses. We have a large GMP facility in the UK with 11 GMP suites and a GMP certificate. But we're not just that. We offer something, I think, beyond that because of the way we've evolved. So we offer end-to-end support. We have technical experts, not just in DNA, but in every application that our DNA is used for. And these guys can support clients from designing the first discovery studies, research studies, comparative studies, all the way through your preclinical, your pre-IND, and IND, and beyond. In addition, we understand the need to support our clients more generally from a product development perspective. So we have a very experienced CMC regs team, and we deliberately recruited a team of product developers into that team who understand the challenges you're going to have to face in your regulatory submissions. In addition, we are the, I think, globally, universally acknowledged leaders in cell-free DNA. We've been around quite a long time. And so we continue to innovate. That's right at our core. We continue to build our IP and patentable IP and know-how. And we continue to design new molecules so that we can keep up with the evolution of a very fast-moving cell and gene therapy space. So why are we in this business? Well, there is an incumbent technology, which we all know, which is plasmid. Those of you who've worked with plasmid supply, either producing it yourselves or purchasing it from a supplier, will know that it's been a workhorse for probably as long as I've been alive in the emerging biotech industry. But there are bottlenecks, and I don't like to be negative about plasmid. It's been superb in facilitating the emergence of the biotech industry. However, there are bottlenecks. There are bottlenecks in terms of moving from discovery through to scale-up development and GMP. These are bottlenecks around scalability, bottlenecks around the requirement for a GMP cell bank, and bottlenecks in terms of regulatory hurdles that you have to overcome. And this is more true, I think, in the cell and gene therapy space than perhaps was typical in the biologics industry. So it's issues around antibiotic resistance genes and origins of replication and what have you. So what do? We make DNA outside of cells. It's an enzymatic process. Essentially, whether we make a mg or we make tens of grams, we use the same enzymatic reaction. We use the same reagents, we use the same materials, and so the process is directly, linearly scalable and is representative of what your final commercial product will be, even at quite a small scale, which really removes a lot of the later bottlenecks you might face at IND stage or BLA stage. One of the other advantages of cell-free DNA, making DNA outside of cells, is that you can make a range of molecules. So we work with a portfolio that consists of a number of molecules. On the left, you'll see dbDNA or doggybone DNA. That's our long-lasting brand, I think you may be most familiar with. So doggybone DNA is double-stranded covalently closed DNA. And this is used by our clients for viral gene therapy, non-viral gene therapy, as a DNA API, and also in gene editing. It's our most established molecule. We also have zdbDNA, which is it's a molecule that's open at the 3' end. It's perfect for IVT, and that's for mRNA, both for personalized medicine, which we see increasing demand for, and of course large-scale production for pandemic response. And then on the right, you can see our most recently launched molecule for GMP. This is a circular single-stranded DNA sequence with a short double-stranded stem, which contains a nuclease binding sequence, whichever nuclease you choose. And that's been designed as a perfect HDR template for genome editing. And because we're in enzymatic DNA, we can make all sorts of different molecules. We've seen a fantastic performance with megabulb DNA in HDR. And because of that, we've sort of built on our portfolio to think about how we could design molecules for alternative gene editing approaches. Perhaps to address some of the weaknesses of a CRISPR-Cas9 system in terms of the size of the gene that you want to be working with, or perhaps you want to go into non-dividing cells. And so we've designed some new molecules which are for example, transposase-based editing, recombinase, perhaps HITI. And so we have a fully single-stranded circular DNA. I would particularly highlight that the sequence is 100% a user-defined sequence. There's no backbone sequences in there at all. We've also designed a hybrid single-stranded circle, we call it. We need to come up with perhaps better names, and better than, more like doggybone, I think, but we haven't quite cracked that yet. So we have a single-stranded circular DNA with short double-stranded sequence regions. And again, that double-stranded region is entirely at the bequest of the client. We can put any sequence in there of any sequence length. And then finally, we've seen an increase in demand for simple double-stranded circles, again, with an entirely user-defined sequence. Obviously, there are double-stranded circles out there that are called plasmids, but this one doesn't have the bacterial sequences in, of course. We are the leaders in this space. I'm not going to bore you by reading out all these numbers, I promise. Just a couple of things perhaps to highlight. We have made many sequences for many clients now. We have fabulous relationships with some major license partners and collaborators. But if I look at these numbers, the one that excites me the most, if you like, is the clinical adoption. We have 7 products in the clinic that use our enzymatic DNA. We have 8 that are going under review. Either they're under review or under compilation. And we've had a DMF filed in the US since 2022. These numbers are continuing to increase and escalate, if you like. We're reaching a sort of exponential phase of overcoming the earlier sort of adoption hurdle of enzymatic DNA. We are becoming the incumbent technology, hopefully over the near term. I should also say that the INDs and CTAs are across a very broad range of applications of DNA. And these are some of the applications that cell-free DNA can be used for. Again, I'm not going to go through them all in too much detail. Perhaps a couple I can highlight are we've made, and as an example of our development status, we've made pivotal enabling dbDNA for an RNA client in cell therapy across their entire platform. We've recently had a client with a CTA approval for a DNA neoantigen vaccine. We're seeing increasing demand in non-viral gene therapy and genome editing, as you can probably imagine. But if I were to sum up a common theme across all these applications, generally speaking, you need less DNA. And there's a very, very simple explanation for that. It's a copy number advantage. When you buy a gram of DNA from a plasmid manufacturer versus a cell-free DNA manufacturer, you're just getting more gene copies for your buck. I'm just going to touch very briefly on some data now. So I've just picked a few sort of data sets. These are all, none of these are Touchlight data. They're data from clients and collaborators over recent years. Here we have a client who was working or is working in AAV9. Like everybody else working in AAV, they're interested in improving their cost of goods profile. I'll just walk you through this slide. On the left is a viral genome titer. Doggybone is in purple, plasmid is in black. We showed a 40% increase in the viral genome titer compared with plasmid, but interestingly, with 40% less DNA and 60% less transfection reagent. In the middle, we have, this is next-gen sequencing. It's nanopore sequencing of the contents of the viral capsid. We show, again, plasmid on the left, doggybone on the right. We saw, or our client saw, a 12% increase in viral genome reads in the capsid in the doggybone versus the plasmid, which is sort of not surprising because our DNA only consists of the DNA sequence of choice. And then, of course, concomitantly, a 12% decrease in process impurity reads. And then finally, on the right, the percentage full. This is mass photometry, which those of you working in, excuse me, in viral vectors will be very familiar with, where at the bottom, plasmid in black is showing 14% full, and doggybone is showing 32% full, so a doubling in the percentage full capsids. Excuse me. Here we have some genome editing data. This is really exciting. This is megabulb data, which I'm very excited about. So here's a client that was interested. Here they're working with primary T cells, so ex vivo T cell editing. And the client was interested to know whether they could improve their donor-to-donor consistency, but then also improve the overall knock-in rate. And here you can see we have megabulb in purple, and then for full disclosure, we have doggybone in blue, and we have plasmid in black. Now, if you eyeball those first three sets of graphs, that's donor A, donor B, donor C. First of all, you can see that the plasmid responses aren't very consistent. For cell-free DNA, we're seeing a much greater consistency of response. But what's really interesting about megabulb is that dose response. The cells can continue to tolerate, and that data aren't shown actually, the cell viability is maintained, but we start seeing really, really impressive knock-in rates. So here we're looking at a knock-in rate of around 70%, and this isn't an unusual data set. Our clients are repeatedly seeing these sorts of numbers. So the demand we're seeing for megabulb is increasing enormously. This is non-viral gene therapy. So this was a client that wanted to know, okay, with doggybone DNA, can you improve the expression profile? Can you also improve the tolerability in an LNP formulation? So here first of all, the graph on the left, you can see at an equivalent dose of, I think it's 0.3 mg per kg, the doggybone is outperforming in terms of expression versus plasmid. But what's interesting, and what we always ask our clients to do, or anybody testing our DNA, titrate down the doggybone. Don't just go head-to-head. Enzymatic DNA behaves differently. You should titrate it down and see how it behaves. And here we can see they've used a third of the amount of doggybone and got equivalent, perhaps slightly better expression rates than the plasmid at 3 times the dose. On the right is a heat map of the tolerability. They looked at inflammatory markers, and they also looked at liver injury markers. And you can see the plasmid at the top. You can see lots of red. That means there's a lot of inflammatory response and liver injury. And then the equivalent dose of doggybone, and at the bottom, the lower dose of doggybone that saw the equivalent expression. So we've seen an improved expression, improved duration, and improved tolerability with doggybone versus plasmid. And what our client is interested in is dose sparing. So that's what they wanted to see. This is dbDNA data. So this is a client who, they didn't tell us they were going to do this, actually. So they wanted to compare us as a supplier, as a platform, versus plasmid, but also against another vendor of a cell-free DNA platform. And here they're comparing two sort of product quality aspects, if you like, of the mRNA that is derived using cDBDNA. First of all, double-stranded RNA, which is shown at the top. I'd just draw your attention to the dot blot because it's visually very easy to understand. We have the doggybone DNA and the plasmid DNA both producing very low double-stranded RNA, and the alternative cell-free platform, and I don't know which it was, and I wouldn't name it if it did, has quite a problem with double-stranded RNA. The client went on to look at the RNA purity, and these figures at the bottom left are based on fragment analysis, and the mRNA was coming out as better quality using dbDNA versus plasmid.
Apologies, we are at time.
Oh, okay. I think that's it, yeah. Okay, so we've run out of time for questions, I think. What I'm going to do is hand over to the next speaker. I'm going to hang around afterwards. My colleague Millie over there with the blonde hair runs our application specialist team, actually, so she's going to be able to help you answer questions as well. But otherwise, thank you.